Welcome back to Bio 6612. This is our last lecture of our introduction to longitudinal data analysis. And in this lecture, we're going to focus on exploratory data analysis for understanding correlations in your data. So there are two parts of the model that you have to specify when you're doing longitudinal data analysis. And this is for specifying a regression model, by the way. The first is specification of the model for the mean. This is the X betas that you put into your model, meaning which X terms, which covariates you're including, and if you're doing things like transforming them, like X squared, or if you're adding interaction terms, stuff like that. So in order to figure out which covariates are good to include, you can do the same sort of exploratory analysis you would perform in a linear regression setting. What's new is specification of the model for the variance. That has to occur in longitudinal data analysis, which doesn't occur in ordinary least squares. And this is where things start to get complicated. For example, what form does the variance take? And what correlation structure, like the ones we discussed in the previous lecture, might be reasonable as a model for your data? So in the next couple slides, I'm going to discuss exploratory analyses and various approaches for describing the structure of the variance. So overall, what are you doing? Well, we want to look at as much of the relevant data as possible rather than just data summaries. And this corresponds to really any exploratory analysis, not just with longitudinal data, but you really want to get a full picture of what's going on in your data before you choose your model. And you want to make note of any unusual patterns or individuals that you might see. First, reviewing what we looked at for the mean. So in lecture 10.2, we looked at EDA techniques for the mean using both the pig weights and the CD4 data sets. One of the things we looked at were distribution plots over time, which are best for balanced data, and those are box plots of the outcome at each time point. We looked at the scatter plot of the response over time, and we looked at spaghetti plots. And for understanding the correlation structure, we're going to look at residual pairs plots, we're going to look at empirical covariance, and we're going to look at the autocorrelation function. And I'm going to focus on the pig weights data here. So first up is residual pairs plots. And the intuition behind this and a lot of the other ways of assessing covariance is we can assess the covariance or correlation structure by examining the residuals. And when we're looking at residuals, that requires us to fit some kind of model. And so the procedure that we're going to take is, in the first step, we fit a very flexible model that captures the mean structure at each time point. Then you save the residuals from the model fit, and you make a scatter plot matrix of the residuals. So I'll do this for the pig weights data. Here, first I'm calculating the mean weight at each time point and subtracting this from the weight value to obtain residuals. So first I load the semipar library so I can load the pig weights data. And then I am defining a pig weights data set by first calculating the mean at each week. That's what's going on in this set of code here. And then I'm calculating the residuals by subtracting that mean value at each time point from the week from the weight. This gives me a new variable called residuals. And I'm also putting that into a new data set. And so then I actually plotted these residuals against the number of weeks here, and you can see that since the mean has been subtracted, we have now like a mean 0 residuals for our data set. So then the next thing we're going to do is transform this residuals data set from long format to wide format. Sorry, so what I have written here is actually not correct. I say the residuals data are currently in wide format. Actually, they were currently in long format, and we need to switch them to wide format. That's just a typo there. I'm also removing the ID because we don't want to calculate the correlation of the ID row. But so here I'm taking the residuals that I calculated in the previous slide, and I'm using the pivot wider tidyverse function to transform this data from long format to wide format. And then subtracting, getting rid of the ID column. So what you end up with is a data set in wide format here where I just have columns from week 1 to week 9, where the values are the value for the residual and each row is a subject. And the reason for transforming it this way is because the types of functions that you use to produce residual pairs plots want the data to be in wide format. So now I'm actually going to make the residual pairs plots using that wide data that we just calculated. And I can do that just using this pairs function on that wide version of the data. And this will produce a scatter plot, several sets of scatter plots where you have a scatter plot for each week against each other week. And that plot is shown here in this slide. And so on the diagonals, that is going to be equal to 1 because we had sigma squared times the correlation matrix. That's what we're looking at right here. So that's why you don't have anything on the diagonals, because that's just equal to 1. So this first plot would be the residuals, the scatter plot of the residuals from week 1 against week 2, all the way up to the scatter plot of the residuals of week 1 up to week 9. And one thing you can see here, and then going down the off diagonal here, the first off diagonal, you have week 2 against week 3, week 3 against week 4. These would be the sort of one distance apart points in time, 1 week apart points in time. And you can see that we have pretty tightly correlated residuals between week 1 and week 2, and between week 2 and week 3. So if you only have 1 week that has passed, the residuals are highly correlated. However, when you get out into the sort of ends of the matrix here, say looking at week 1 versus week 7 or week 1 versus week 8, the plots are not as correlated, which indicates that the correlation within a subject is less strong as you go farther out in time. So empiric correlation is similar to what we just looked at, but this is just a way of calculating the correlation that you see based on the residual matrix that we have. And we can calculate it by just taking the core function of that Y matrix we calculated. And then I'm actually only looking at the correlation for the first 5 weeks here, just because it fits nicer on the slide. It's not quite so big. But if you wanted to look at the correlation, the empirical correlation for the whole data set, then you would just get rid of this bracket. And And what you can see from the matrix that's pointed out, of course, it's ones on the diagonal, so we ignore that. That we have a very high correlation between week 1 and 2, high correlation between week 2 and 3, high correlation between week 3 and 4. Basically, correlation is higher at time points that are closer together, which is the same thing that we saw in the plot of the residual pairs. But then as you get farther out, like week 5 against week 1, we have a correlation of 0.75, which is smaller than we see along the diagonal. And this trend sort of like week 1 versus week 2 is the highest, week 3 versus week 1 is a little bit lower. And what this says to me is some sort of autoregressive or exponential correlation structure, something that allows you to calculate correlation that is highest at time points closest together and gets progressively less correlated, is something that might make sense for this data. I'm going to go back to the residual pair plots just for a minute, because you can calculate those using a GG plot type function instead, and I think this version is a little bit nicer. And you calculate that using the GG pairs function from the GG Galley library. And you would do it produce it the same way. Here I'm taking the pig residuals wide. If you want to do pairs for all the time points, you would just put in that data set. Here I'm only doing it for the first 6 time points because it's just easier to fit it on the screen. But if you would normally want to look at the whole data set, so you would not exclude that bracketed part there. And so what that plot looks like is you have all of your pairs here, your residual pair plots. And so this is going to be symmetric matrix, so you don't have to have this point at week 1 versus week 2 would be the same up here. So instead of just putting the same plot in that space, instead they give you the actual correlation between week 1 and week 2. And they also give you a histogram of the residual values at that particular time point. So it kind of gives you like the best of both worlds when it comes to the empirical correlation and the residual pairs plot. And this shows you the same thing that we've seen, that if you have time points that are closer together, which are these here, those tend to have higher correlations. And then the time points that are farther apart, these have lower correlations. And finally, the last plot that we're going to talk about is the autocorrelation function. And this is the autocorrelation function is a function that summarizes the correlation in residuals measured at time lag u. So basically the correlation between the jth time point and then the j plus uth time point. Lag being, okay, if I have time point 1 and time point 3, then u is equal to 2, so the lag is 2. If I have time point 1 and time point 5, then u is equal to 4, so lag would be 4. And generally speaking, with longitudinal data, you think larger lag tends to mean less correlation. And this function is most appropriate for data where the residuals, meaning the outcome values, are spaced equally in time. And also the residuals have roughly mean 0 and the same variance at each time point. So how do we know if residuals have roughly mean 0 and the same variance at each time point? Well, I'm just going to calculate this for the pigs data by grouping by the number of weeks and then by grouping by week and then calculating the mean and the variance of the residuals at each week. And that's printed out on the next slide, but what you'll see is that for this data set, the residuals do have mean 0 at each time point, but the variance tends to increase as the number increases. So this is actually the autocorrelation function might not be as appropriate for this data set since the residuals don't have the same variance at each time point, but we're still going to use it anyway. So here is that table looking at the variance at each time of the residuals at each time point, and you can see that the variance is increasing with each week for the most part. Okay, so how do you actually estimate the autocorrelation function? There are a few ways to do this, but the one that I use most often is from the using the NLME package, which stands for Nonlinear Mixed Effect Models. And this package will come up throughout the rest of the semester when we look at linear mixed effects models. And then the first thing you do is you fit a model to the data. This is a generalized least squares model where you're fitting the outcome against the time variable as a factor. And this is like a fancier way of fitting a mean model than we did when we fit a model to the PIGS data before. That's really what is going on here. We're not going to talk about generalized least squares in this course, but if we did, generalized least squares is basically linear regression where you relax the independence assumption for your errors. So you fit your GLS model, that's just going to give you some different mean at each of the different time points, and then you apply this ACF autocorrelation function to your fitted data. And then to actually get a plot, I'm going to produce two different plots, but one of them I'll make in ggplot where we look at the lag on the x-axis and the autocorrelation function that's calculated on the y-axis. And so let's talk about that first. That plot is here. So as lag increases, meaning as distance between time points increases, the autocorrelation function is decreasing. So that just means that time points that are farther apart tend to be less correlated. And similarly, we can look at this other version of the same plot, which is interpreted in a similar way. You have lag on the x-axis and then spikes at each for the autocorrelation at each of the different lag points, where the higher the spike, the more the autocorrelation. And this also tells you that points are less correlated as they're farther apart in time. And that's it for this week. Next week, we're going to discuss at a high level a few different models for longitudinal data, in particular marginal versus random effects models. And then we're going to start learning about random effects models, also called linear mixed models, by the way, in more detail.